In the last few years, the energy transition stopped being a policy slogan and became an industrial throughput problem. In 2024, global renewable capacity additions surged to roughly 700 gigawatts, and solar alone accounted for about 550 gigawatts of new capacity in a single year, pushing global installed solar PV capacity to roughly 2.2 terawatts. Those numbers describe a manufacturing system that now moves at the scale of heavy industry. They also expose a constraint that is easy to miss in headline narratives. Modern solar is built on a thin layer of high-conductivity materials, and one of the most important of those materials is silver. Silver is not used in solar because it is scarce and expensive. It is used because it is electrically efficient, corrosion-resistant, and reliable in the metallized contacts that move electrons out of the cell through interconnects and into an electrical system that cannot tolerate failure. When a technology scales from gigawatts to terawatts, even milligrams per watt become thousands of tons per year, and that arithmetic is the starting point for understanding why 100% renewable targets collide with the physical realities of a metal that must also serve electronics, grid hardware, vehicles, and a growing layer of data infrastructure. The solar transition is therefore not only about panels, inverters, and land. It is also about how much silver the world can produce, where it comes from, how quickly it can scale, and what happens when a key industrial input is pulled simultaneously by multiple sectors that are expanding at the same time. The first step is to put the solar-silver linkage in concrete units. Industry roadmaps that track photovoltaic manufacturing inputs express silver intensity in milligrams per watt, and those milligrams convert directly into tons per gigawatt. A useful equivalence is that 1 milligram per watt equals 1 ton per gigawatt. At 10 milligrams per watt, 1 gigawatt of cells implies about 10 tons of silver. At 8 milligrams per watt, 1 gigawatt implies about 8 tons. The precise number varies with cell technology and metallization design, but the unit logic is stable. Now apply that to the scale of the 2024 solar market. Solar deployments and shipments differ, but both describe the throughput of the industrial machine. When the world installs on the order of 550 gigawatts of solar PV in a year, and if silver intensity is on the order of single-digit to low double-digit milligrams per watt, the annual silver requirement for solar alone lands in the thousands of tons. That is not a theoretical estimate. Public market surveys of the silver industry show photovoltaic demand for silver around 200 million ounces in 2024. 200 million ounces is not an abstract number either. It is roughly 6,000 tons of silver locked into a single end-use category in a single year, and it represents a material claim on global supply that must be met alongside all other industrial and non-industrial uses of the metal. The next step is to anchor supply. Global silver mine production in 2024 is estimated at about 25,000 metric tons. That is the annual flow of newly mined silver into the world economy before recycling and inventory movements. Convert 25,000 tons into ounces, and it is roughly 800 million ounces of mine output. That means that solar's annual pull, on the order of roughly 6,000 tons in 2024 by published market survey figures, sits as a large fraction of yearly mine production. It is not the majority of supply, but it is large enough that small changes in solar growth rates or silver intensity matter at the level of thousands of tons. This is the core reason the green transition can face a silver constraint without any dramatic shortage narrative. The math is tight because the throughput is enormous, and the constraint becomes more visible once the rest of the demand stack is included. Industrial silver demand overall reached a record level in 2024 according to published market surveys, while total silver demand across all categories was about 1.16 billion ounces in 2024. On top of that, the same surveys describe multiple consecutive years in which demand exceeded supply, resulting in structural market deficits. A deficit does not mean the world ran out of silver. It means the difference was met by drawing down inventories, recycling flows, or other forms of supply, and it means the system is operating in a way where buffers matter. The question is not whether silver exists in the Earth's crust. The question is whether the accessible, economically extractable flow, year after year, at the necessary purity and reliability, can expand fast enough to meet the planned build-out of solar and the other systems that compete for the same metal. This is where the mathematical calculation becomes less of a slogan and more of a framework. The energy transition pathway that many institutions describe is not more solar. It is massively more solar. For example, a 1.5 degrees Celsius pathway published by a major renewables agency describes global installed solar PV capacity rising to well above 10 terawatts by mid-century, and one published pathway places the 2050 figure above 18 terawatts. Compare that to the roughly 2.2 terawatts installed by 2024, and the scale of expansion becomes clear. The world would need to add something like the entire existing global solar fleet multiple times over within a few decades. That expansion is not only panels. It is wafers, cells, paste, metallization lines, glass, frames, inverters, transformers, cables, and grid connection hardware. Silver sits in multiple parts of that chain, but the best documented linkage is in cell metallization and interconnects. So take a simple scenario. Assume global solar PV installed capacity rises from about 2.2 terawatts to about 18 terawatts. That is roughly 16 terawatts of additional solar. The metal content of that additional capacity depends on silver intensity at the time of manufacturing. If silver intensity averaged 10 tons per gigawatt, then 16,000 gigawatts would embed about 160,000 tons of silver into the solar fleet. If intensity averaged 8 tons per gigawatt, then the embedded silver would be about 128,000 tons. If intensity averaged 12 tons per gigawatt, then it would be about 192,000 tons. These are large numbers, but they're not impossible relative to known global reserves. Published reserve estimates by geological agencies place global silver reserves on the order of hundreds of thousands of tons. However, the reserve comparison is not the main constraint. The binding constraint is annual flow and competing demand, because the transition requires sustained high annual installations for decades, and because silver embedded in panels is effectively removed from circulation until panels reach end of life and are recycled at scale. In other words, the transition is not primarily competing with a static stock of silver. It is competing with the rate at which silver can be mined, refined, allocated, and then later recovered, while also serving other strategic sectors. This is why the claim "there isn't enough silver" is better translated into a more precise statement. The combination of required annual solar additions, realistic silver intensity, and simultaneous growth in other electrical end uses implies a large and persistent claim on annual silver supply, and the system must solve that through a mix of higher mine output, higher recycling, faster thrifting, substitution, and different technology choices. Solar is also not a stable technology in terms of silver intensity. The PV industry has a long history of reducing material inputs through design changes, better printing, narrower lines, more bus bars, and new metallization approaches. Published research and industry roadmaps describe significant thrifting progress in recent years, including sharp reductions in silver loadings in 2024 and expectations of further reductions thereafter. This means that the solar-silver constraint is dynamic. A decade ago, the silver content per watt was higher in many mainstream cell types. Today, industry roadmaps discuss remaining silver per watt in the single-digit to low double-digit milligram range for major technologies, and they also discuss pathways to reduce further through copper plating and silver-coated copper approaches. The existence of thrifting is not a reason to dismiss the constraint. It changes the slope of the equation, not the structure of the equation. If installations rise faster than intensity falls, total silver required can still rise. If intensity falls faster than installations rise, the silver requirement can stabilize. The question becomes a moving target that depends on technology mix and deployment speed. That is why a credible analysis must include both sides of the equation, the scale of solar growth and the pace and limits of thrifting and substitution. A useful way to visualize this is to anchor on annual solar additions. Suppose annual global solar installations remain in the neighborhood of 500 to 600 gigawatts per year, consistent with the high levels seen in 2024. At 10 tons per gigawatt, solar would require roughly 5 to 6,000 tons of silver per year. At 8 tons per gigawatt, the requirement falls toward 4 to 5,000 tons per year. At 12 tons per gigawatt, it rises towards 6 to 7,000 tons per year. Now compare those numbers to annual mine production of around 25,000 tons. Solar alone would represent something like 16% to 28% of mine output in these rough ranges, before considering jewelry, silverware, electronics outside PV, brazing alloys, chemical uses, and investment demand that can rise and fall with prices and macro conditions. This is why published market surveys note that industrial demand has been setting records even when other categories soften. The industrial portion is tied to system buildouts that are multi-year and often policy-influenced. Solar is one of the largest of those buildouts, but it is not alone. The green transition is also a grid transition. Solar and wind additions require transmission expansion, distribution upgrades, and a large increase in power electronics. Every added gigawatt of variable renewables increases the demand for switchgear, transformers, relays, connectors, and control systems. Silver is used in many of these components because it performs well in contacts and conductors. Then there is electrified transport. EV adoption increases the electrical content of vehicles. Inverters, converters, battery management systems, onboard charging, sensors, and high current switching. Even if per-vehicle silver use is modest in absolute grams, the volumes are large when global auto sales scale into tens of millions of vehicles. A third layer is data infrastructure. AI and cloud buildouts increase demand for servers, networking, and power distribution equipment. That pulls silver through electronics and through the power channel because high-density compute requires reliable, high-quality power delivery and local grid upgrades. The key point is that solar does not compete for silver only with jewelry. It competes with a growing stack of electrification and digitization hardware that is expanding for reasons that are independent of solar. The interaction of these sectors changes the risk profile of the supply chain because it reduces the amount of slack in the system. If one sector slows, another can still pull. If all expand, the system needs either more silver or less silver per unit of output across multiple industries at once. That brings the analysis to supply structure. Silver is not mined the way iron ore is mined. A significant portion of global silver production is byproduct output from mining of other metals, including lead, zinc, copper, and gold. This matters because it makes silver supply less responsive to silver price signals than a metal that is mostly mined as a primary product. If a copper producer expands output for copper demand, silver output can rise. If a copper producer slows, silver output can fall even if silver demand is high. If a primary silver miner wants to expand, it can face permitting timelines, capital costs, and geological constraints. This structural characteristic makes just mine more silver a slow lever. It also means that the solar silver constraint cannot be solved by assuming a fast supply response. Instead, it tends to be solved by a combination of incremental mine growth, recycling expansion, and changes in intensity and substitution. Recycling is often presented as the release valve, but it has timing issues. Much silver is embedded in long-lived products. Solar panels are built to last decades. That implies that large-scale recycling of solar silver depends on the age profile of installations, collection systems, and economic incentives. In the near term, recycling contributes, but it does not instantly return the silver embedded in the newest wave of installations. That creates a temporal mismatch. The transition front-loads material demand, while recycling returns material later. This is a common feature of infrastructure buildouts. It is why shortages can occur even when long-run recycling potential is large. There's also the issue of recoverability. Recovering silver from complex products is technologically feasible, but depends on process economics, regulatory frameworks, and industrial capacity. A system that aspires to run primarily on renewables must therefore plan not only for manufacturing and installation, but also for end-of-life processing at an entirely new scale. This is where the 100% renewables narrative meets the industrial planning challenge. The target implies a complete transformation of power generation and an expanded grid, but the materials side is often treated as a footnote. Silver is one of the metals that turns the footnote into a hard constraint because its use is concentrated in exactly the kinds of interfaces that cannot be easily compromised without affecting performance and reliability. The PV industry's thrifting efforts show that engineers can reduce silver per watt, but those reductions can have limits that depend on contact resistance, durability, yield, and the economics of new processes. Copper plating is one of the major substitution pathways discussed in industry roadmaps. It can reduce silver dependence, but it also introduces new process steps and quality control challenges, and it shifts dependence to copper supply and to the chemicals and equipment needed for plating and barrier layers. In other words, substitution is not free. It trades one set of constraints for another. Still, substitution is a real lever, and a realistic analysis must treat it as a central part of how the system adapts. The point is not that the transition is impossible. The point is that the transition is an engineering and supply chain problem as much as it is a policy problem, and silver is a measurable indicator of that reality. The next step in a rigorous mathematical view is to connect the demand pathway to the mining and reserve numbers without turning it into a false binary. Geological agencies publish reserves as economically recoverable material at current prices and technologies. Global silver reserves are large in absolute terms, but they are not infinite, and they are not evenly distributed. Major reserve holders include countries that are also central to broader geopolitical and industrial supply chains. Production is concentrated, and refining and fabrication capacity can be concentrated as well. This creates a second kind of constraint, geopolitical and logistical constraints. Even if global reserves exist, the transition requires a reliable supply of refined silver in the right form, delivered into industrial ecosystems that are producing cells, electronics, and electrical hardware at scale. Trade barriers, export restrictions, refinery capacity constraints, and transportation bottlenecks can all translate a global resource into a local shortage. That matters because solar manufacturing is geographically concentrated and because strategic competition over industrial supply chains has increased. When an input is both industrially critical and globally traded, and when supply is concentrated, the system becomes sensitive to policy and trade decisions. The transition therefore runs through not only geology and engineering, but also trade policy and industrial strategy. Now place all of this back into the 2024 baseline. In that year, solar PV additions were roughly 550 gigawatts, and industrial silver demand reached a record level in published market surveys. At the same time, those same surveys describe a multi-year pattern in which silver demand exceeded supply, implying ongoing deficits that were met by inventory drawdowns and other sources. This pattern matters because it indicates that the market was not operating with large excess capacity. A market with abundant slack can absorb demand surges without major stress. A market that has been running deficits for multiple years is more sensitive to shocks, whether those shocks come from demand acceleration, supply disruptions, or policy actions. The solar transition is built on long lead times, and mining expansions also operate on long lead times. When both the demand side and the supply side are slow-moving, short-term imbalances can persist for years, and the system's adjustment tend to happen through a mix of higher prices, substitution, and rationing by priority. Even without discussing price outcomes, the mechanism is structural. When a critical input is constrained, high-priority uses tend to be served first, and lower-priority uses either pay more, substitute, or delay. In a world that wants rapid electrification, the competition for high-conductivity materials becomes a competition between different electrification channels. Solar panels compete with grid hardware, EV production competes with consumer electronics, and data centers compete with industrial power equipment. The silver constraint is therefore not just about solar. It is about the entire electrical interface layer of the modern economy. At this point, the phrase solar collapse can be reframed as an analytical question rather than a prediction. The relevant question is not whether solar will stop. The question is whether the speed and scale of the planned transition can be achieved without encountering material bottlenecks that force trade-offs in timing, technology, and cost. Silver is one of the best case studies because the numbers are public, the usage is measurable, and the industry openly discusses thrifting and substitution. If solar capacity must expand from a few terawatts to well over 10 terawatts, and if annual additions must stay in the hundreds of gigawatts for decades, then even a low single-digit milligram-per-watt silver intensity translates into thousands of tons per year. If, at the same time, industrial electrification and data infrastructure continue to expand, the demand floor for silver can remain elevated even when consumer categories fluctuate. That is the logic chain. It does not require claims about secret stockpiles or sudden depletion. It rests on unit conversion, deployment data, mining output, and published industry demand numbers. There is one more layer that often gets overlooked in public debates about material constraints: the difference between installed capacity and effective energy delivered. Moving toward 100% renewable electricity is not the same as installing a nominal capacity number. It requires storage, grid reinforcement, and redundancy to handle intermittency and seasonal patterns. Those additions can increase the hardware intensity of the transition, and therefore the material intensity. Even if solar becomes cheaper per watt, the system-level build-out can still demand more physical equipment per unit of reliable delivered energy. That can indirectly raise demand for metals used in electrical interfaces. Silver is not the dominant metal by mass, but it can be a dominant metal by functional criticality in specific components. That is why it matters when policymakers and commentators discuss the green transition. The focus often stays at the level of megawatts, emissions, and financing. The deeper constraint is industrial. Can the world expand the physical backbone of an electrified economy fast enough, using materials that are mined and processed through real bottlenecks? Solar PV is one of the fastest scaling technologies in history, but its scaling is still bound by materials. The published 2024 data show that solar alone already commands on the order of 200 million ounces of silver demand, that global solar additions have reached levels around 550 gigawatts per year, and that global mine production is around 25,000 tons per year. They also show that the silver market has experienced repeated deficits in recent years, meaning that part of the system's balancing has relied on inventories rather than new production. At the same time, industry roadmaps and surveys show that PV manufacturers are reducing silver loadings, which is an adaptation mechanism that can slow the growth of silver demand per gigawatt. The transition's feasibility, therefore, depends on a race between three timelines: the timeline of PV deployment, the timeline of metallization, thrifting, and substitution, and the timeline of mining and recycling expansion. None of these timelines is instantaneous. PV deployment is fast, but it is constrained by grids and permitting. Thrifting is continuous, but it has engineering limits and requires capital investment in new processes. Mining and refining are slow, and recycling depends on installed base age and collection infrastructure. When those timelines are aligned, the transition runs smoothly. When they're misaligned, the system experiences bottlenecks. That is the measurable, data-driven meaning of the silver question. The green transition is not simply a matter of wanting more renewables. It is a matter of building an electrical civilization at scale, and that civilization is assembled out of finite flows of industrial materials. Silver is one of the clearest indicators that the transition has entered the phase where material arithmetic matters.